Okay? Now notice that each processor has a memory, so you can store m elements. And notice that therefore we have p times n elements that can be stored, but we need to store that matrix. We'll ignore the vectors. So the maximum that we can store, we can give by the square root of p times square root of m. And then if we look at the efficiency, the realist would say each processor can only store m elements, so we're going to scale n according to that. And the question then is it efficient if we scale the problem as we can? And the answer is that if you manipulate this, you end up with a constant. That's this memory per processor divided by that. But there is the square root of p here. And notice that if p gets very, very large, your efficiency goes to 0. So this is a bad algorithm. Okay, and you can say, well, I guess we can't do a parallel matrix vector multiply on these huge machines. Why is NSF wasting its money on them? And you're going to say, well, this is one algorithm. We taught you many algorithms in this course. So we could simply say, oh, we'll just look at the matrix vector multiply that works by columns using Axpes. And that, just to remind people, you march through, and every time you do a column times a scalar, and you add that to the result, you march through that, etc. And then we can slice and dice this by saying you take your matrix A, you partition it into p blocks. You do the same thing with the vector x. And then if you do a partitioned matrix vector multiply, which we talked about in week 4, I think, you end up with this expression right here. And then if we illustrate this, so then you recognize that maybe the subproblem can be computed on processor J, and then it's a matter of taking local contributions and adding those together. And of course, there's some communication that happens there, and we're going to ignore the cost of that. So you can picture that as here are your matrices, here are your subvectors, and then you want to compute local contributions, and then you need to add them all together. Okay, very straightforward. If you do the cost analysis of this, actually the cost analysis is absolutely identical if you ignore communication, because the extra cost comes from the communication. But the extra cost in the communication is actually roughly the same for the two. But let's not get into that. So the bottom line is that the optimist says it's great, the pessimist says it's bad, and there's this scalability issue, and then the realist will say, well, it's still bad. Okay? So partitioning in matrix by columns is not good. Partitioning in the matrix by rows is not good. What are we to do? Well, we also did 2D slicing and dicing, and that was in week, I think, 4, maybe 3. And we learned that you could do a partitioned matrix vector multiplication by simply thinking of these blocks as being elements and multiplying everything together. And what we can do is we can say we have p processors. We'll view them as a square root of p by square root of p mesh. And let's see what we can do. Well, we learned that when you multiply this together, you get this expression right here. And now we have p tasks, square root of p per line that we have here, that can all be done in parallel. Let's see how that works out. And obviously, there's some communication that needs to happen. There's some summations across processors that need to happen. And we're just going to ignore that to get some idea of whether this might be a good idea. So just to illustrate this, here we have the matrix distributed. Here we get our vector already properly in place. We get local contributions that get computed, and then you add them all together. All right, so if we do the cost analysis this time, we still have the same sequential cost. We now get this ceiling function right here, and I actually took the size of the matrix to be now k times the square root of p plus 1, but let's not get into that detail. If you work it out, you get this, you get that speed up. If we then look at the efficiency, you get that, and if we then work with that a little bit, we end up with that expression right there. If we carry that over here, so this is the same expression as at the end, and I'm videotaping this, so if someone really is interested, they can pause this and go through this very, very slowly. The important thing here is we can bring the n to the bottom, cancel, and we get this right here. And now the question becomes, is the optimist the pessimist, well, we don't really care that much about the optimist and the pessimist, but we really would like to make the realist happy, right? So let's see what happens. Here's our efficiency, if you believe my math. And by the way, people who took my course noticed that I make mistakes all the time, so who knows? I did this late last night. Okay, the optimist will still say that you just let n get large and then you get efficiency of 1. The pessimist will say fix n, let p get very large, and then you get no efficiency whatsoever. And then the realist will say, okay, we know that we have p times m in memory, which would be the square of the maximum size of the matrix, which we will make a function of p. So if you manipulate this, you can bring this to the other side. That's what you get. If you then take that and you plug it in here, you get 1 plus some constant. Okay, so as p now increases, the efficiency is constant, and therefore it may just be that this will work. Now obviously along the way we've completely ignored the cost of communication, and you would have to go and learn about what the cost of the communications are that you would run into. But at least we have some hope that by slicing and dicing in 2 dimensions instead of only 1 dimension, we might end up with an algorithm that would make a supercomputer happy. And the good news with that is that then the University of Texas can apply to NSF for an even bigger machine, because after all, we know how to do a matrix vector multiply on it. That's good. All right. So in summary, so in the course, the videos tended to end with a summary, and I'll just keep the summary clean. Slicing and dicing, first of all, allows us to very elegantly describe how to parallelize a matrix vector multiply. We noticed that if you slice and dice only by rows or columns, then it's not what's called weakly scalable. And then if you slice and dice by rows and columns, then it's possibly scalable. Okay? And depending on how nitpicky you are, there's still a slight technicality that gets in the way, or you can say, well, the technicality is kind of insignificant, and therefore we'll just declare it to be scalable for practical purposes. So, since I tend to end my videos with this kind of summary, I think that we should end with it now. Now, at the end of the video, we did not make pizza available to the participants. We do to you, but maybe before that I can take a few quick questions. Any questions? Yes, Alan.
Robert,
this is, by the way, kind of a flashback to when you sat in on my course my second semester as a professor.
a long time ago.
That was a long time ago, wasn't it? Anyway, go ahead.
We should do this again.
Or the MOOC?
Yeah.
So,
knowing what you know now.
You should, definitely.
So, the way I describe it, and some people may take offense at this, is that, we're told that the human race still exists because women forget the pain of labor and the pains of carrying a child. And then they have more children, and therefore we're still here. I think you need to ask that question, 3 months from now. I don't think I'm prepared to answer that right now. I think it's definitely the case that my students will rebel if I do. I think that this took a tremendous toll on them. They want their advisor back, and I think they have a right to have their advisor back. Yes?
This is about the technical content.
Okay.
How typical do you think these gigantic matrix vector multiplies are in practice? I feel like more often you see people who don't have 500,000 cores available, and so they tend to factorize their problems so that they're dealing with much smaller matrices that can be farmed out to smaller machines.
Well, there are lots of answers to this. First of all, the first question really is, how often is a matrix dense, meaning that it doesn't have zeros in it that you can take advantage of. And if that's one question, and then you can say, well, there are these n-body problems which are really matrix vector multiplies, but then there are fast multipole methods that can be used to actually sparsify those, and then this doesn't really happen. However, the theory that I presented carries through when your matrix is randomly sparse, and therefore you can't take advantage of the sparsity. And then all of a sudden, Google will be able to hand you some very large sparse matrices with which they would want to do a sparse matrix vector multiply. So the ideas behind all of this carry through, but obviously I picked a very simple example to illustrate some of the issues. And I was trying to connect to material that they had seen in the class. But you have a very valid point, and probably answering that fully would draw in Victor, who would say I'm all wrong, and this is probably not the place. Okay. Again, the same answer as Alan. Ask me again 2 months ago, 2 months from now, and maybe I'll want to get into a discussion with you. All right. Anyone else have a question? Yes.
Does your code run on the mix at Stampede?
So right behind you sits Tyler, who can actually squeeze about 85% out of the mic processor doing matrix-matrix multiplication. So the techniques that you saw in week 5 apply to the mic architecture, which is also known as the Xeon Phi, which has 60 cores. Now, the scalability argument there is very different, because first of all, the chance that we'll have an infinite number of cores on a single chip is pretty slim, probably. But then that's what we said about distributed memory architectures at one point. More importantly, your memory size is fixed as you add more cores. And that, of course, changes the entire argument. All of a sudden, you become a pessimist. All right, any other questions? Well, I'm hungry. You should be hungry. All right, thank you.